So, hexprimes. I'm not a terrific mathematician yet. More of a fiddler, more of a just throw stuff at the wall, see what sticks kind of guy. So, let's talk about prime numbers. Pretty much, I'm sure almost everyone here knows what a prime number is. It's basically a number that just you can only divide by itself and 1 if you want an integer. So I don't like this definition very much. It's not fiddleable. I can't really play with it. So let me propose a new way to define prime numbers. It still hits all prime numbers, don't worry. So the area of an integer-sided rectangle where one side has to be 1. So just a quick overview. So 12, as you can see, these blue boxes on the side. If someone says, draw me an area with a rectangle 12, you can say, okay, 4 by 3, 2 by 6, etc. But if someone says a rectangle of area 13, you have to do a 13 by 1 rectangle. And because you're forced to do a rectangle in which one side is 1, you know 13 is prime. By the way, this 13 is my extremely lazy, like it used to be 11, but then someone was like, oh, you have to put in 13. So I was like, okay, all right. Yeah, so this definition is a lot more fiddleable. So we can change the word rectangle to hexagon or triangle and see what sort of interesting structures pop up. And so I'm going to keep things equiangular just because the thing that rectangles are known for is that they all have the same angle. So it doesn't leave us a lot of leeway with triangles because an equiangular triangle is an equilateral triangle. But for hexagons, as you can see, this funky hexagon here, weird and still equiangular. All right, so triprimes turn out to be kind of boring because you're looking for triangles with force the side of 1, and the only one that has a force side of 1 is 1. So these black circles represent the areas of these triangles. So you see these numbers here, the ones that aren't the smallest triangle, are tricomposites, if you will. You can denote them as triangles with non-one side. And everything else doesn't really fit into this. But hexprimes, it turns out, are really cool because these, okay, so going from left to right, you can see 1, 2 representations of 3, 2 representations of 4, 5, 6. There's plenty more representations, but I didn't want to draw them all out in PowerPoint. So as you can see, all of these have at least one side that's tiny, one side that's length 1. And many of you sticklers in the audience will have noticed I'm playing a little fast and loose with the rules. This is not a really good way that I could find to break up weird-shaped hexagons into equal areas. So I just went with like this circle filling metric for an area. So ignore all the little spaces between the circles. They don't matter. Okay, so all these are primes. And then that gets us to our first hex composite, 7. 7 is a hex composite because you can draw it as this hexagon, which doesn't have 1 for any of the sides. Cool. So now we can start to say, okay, how many other numbers are hexprimes or hex composites? What can we do with this? And turns out, normally if you have a rectangle or something, you can just put another rectangle right next to it and say, okay, that's a bigger rectangle. I can put 2 rectangles together to make a rectangle. You can't do that with hexagons because the symmetry doesn't work that way. So, but what you can do is you can add layers, you can add rows. So it turns out what this does is you can generate more hex composites by just adding 3 to 7. So now we know that all 1 mod 3 numbers that are greater than 7 are definitely hex composites. And this gets out of hand very fast because, as you can see, we can add 4 in a different direction, and now you know that all 2 mod 4 numbers greater than 10 are definitely hex composites because you could just keep adding layers and get a huge hexagon with definitely no sides that equal 1. So using these and abusing them, we can show that every number above 17 must be a hex composite. So there is a small, finite number of hex primes, and after that, it's a matter of doing an annoying proof, which take too long to explain here, but I can go over it afterwards if anyone's interested. To show that there's exactly 10 hex primes, and they are listed here. So what does all this mean? So this leads us back to an interesting conclusion about regular primes, or rect primes as I call them. Triangles, you have a very easy, the triangle numbers are what are the composites. Everything else is prime or not really classified. So that's a very easy progression. You know exactly, you can give me any number and I can say immediately whether it's a prime or not. Hex primes, I can also say that for any number because all I have to do is check my list of 10, and if it's not in that list, it's a composite. like rectangular primes, which is like the midpoint between triangles and hexagons, is in this weird, interesting place where primes are still unpredictable, and like there's an infinite number of primes and an infinite number of composites, and that's just really interesting. And that pretty much concludes it. My name is Spandan. It's the only name I've ever seen that can be written as an integral. So, and that's it. Thanks a lot.